Hello everyone. Uh, this work is focused on a metamorphic complex located in the eastern portion of Mexico, and it's a fully deformed assemblage of meta-sedimentary, meta-volcanic lastic, and meta-igneous rocks called the Teziutlan Metamorphic Complex. This complex has scarce research studies, but recently there are new data about the origins of the protoliths of these rocks, which was associated to a Bacar basin. Some of the aims of this study was the characterization of the shear zone, also identify the deformation mechanisms and their spatial distribution, and also find about the temperature ranges and age of the deformation. Lastly, we propose a paleogeographic and tectonic model for this complex. So this is a field study work which was in which we identify we made a characterization of the macrostructure and integrated with microstructure analysis. So the Teziutlan Metamorphic Complex is defined by 4 lithodemes. Structurally, from bottom to the top are La Soledad lithodeme, which are mainly composed by these orthonices of plagioclase, quartz, muscovite, and epidote, overlaid by a second lithodeme called Chihuahua, which is made by quartz, muscovite, plagioclase, and chlorite schist predominantly. And over these are the rocks of the lithodeme Cosolesco, which are actinolite, chlorite, albite, epidote, and biotite schist, and also intercalated with these greenstones of epidote, paleozoic, and actinolite, which have no deformation at all. At the top of the complex is the El Mirador, which is formed by a muscovite, chlorite, and biotite schist intercalated with meta-volcanosedimentary rocks. Here is the map of the Teziutlan Metamorphic Complex, and here I show the spatial distribution of the units, where at the north is located the bottom of the structural of the complex, and at the top is the top of the complex. So we identify 4 structural phases, which I resume in this table. And the first 2 set of the structures were developed during progressive deformation of a first phase of deformation, which took place in a plastic regime. The third structure set was formed in a brittle plastic regime, and the 4th set was formed in brittle conditions. So in this talk, I will only focus on the first 2 sets of structures, which I show you here. So this is the general structure of the Teziutlan Metamorphic Complex, and in the gray zones, I point the Mylonitic zones, which are primarily located at the contacts of the lithodemes. And in these places, there are high strain rocks of both lithodemes, but also we find places outside these zones with some strain deformation localization, like in this in this photograph, which I show you a plagioclase-rich layer, which has less strain than the quartz and muscovite-rich layers. So, here I show you some of the high strain lithologies. In C, you can see the orthonices myloniticite with this porphyroclast and sigmoid quartz, and you can also see the differences between the potassium feldspar rich layers and the quartz rich layers, which has more fine grain. Also, the schist develop a strong lineation made by quartz, and the mafic lithologies has these lenses of epidote with isoclinite holes developed. So some of the microstructural textures that I found was, for example, this one, which has a folded foliation with a second foliation superimposed to this first foliation. And you can see in the B picture that the differences between the mechanical behavior of the minerals, like this plagioclase, which has microfractures, while the quartz has dynamic recrystallization or by subbrain rotation and some bulgings. Also, the Mylonitic schist has sigmoids of quartz with subbrain rotation, and in the boundaries has bulges. Some of the most strongest foliations, rocks foliated, was this made only by muscovite, in which we can observe these pyrite crystals with strain pressure shadow. With all these lithologies, we can make a good characterization of the quartz CPO. So we made these samples, which we sample a total of 5 rocks for EBSD measurements, and within the Mylonitic zone, and I took one outside this Mylonitic zone. So the aim of this method was characterize the active slip system during the deformation and the Z-axis opening angle. So we found 2 types of patterns, and we have this one with the cross-gyral type 1, which is result of the active systems of basal A and ROM A, which is has a temperature associated temperature interval of 400 to 500 degrees. The other pattern that we found was this, that is a single zero, and this is the result of the slip system basal A, which took place at a temperature of 300 to 400. So with the cross-gyral type 1, we could measure the opening angle of these polar distributions, and we can estimate the deformation temperature with the quartz deformation thermometer. So we have a temperature between 420 degrees and 427 degrees, which are in good agreement with all the microstructures seen in all the metamorphic complex. So, well, for the first one set of structures, we have these relic minerals of this paragenesis made by hornblende, epidote, plagioclase, and chlorite. So this is this points to a green schist to amphibolite transition between 0.45 and 0.55 gigapascals and 450 and 550 degrees. For these structures, I made an estimation using this gradient for a Bakar basin. Maybe this is a coarse estimation, but I think it works well for a good approach, a good first approach. So this is the cross depth that I estimated for this set of structures. Then we have the second set of structures that we estimate the deformation of temperature of this structure with the quartz thermometer, and we have these values of temperature, and these took place at a deep level of 30 and 17 kilometers. And also these mineral assemblage that grows in these structures correspond to a green schist spaces. So I modeled this one of these rocks, and I found a big stability field for this paragenesis, and which is in good agreement with all of these estimations. So for the deformation age, we have a good constraint with the zircon edges of zircon magnetite edges from metatonalite of one of the lithodemes, which gave us a minimum crystallization for the protolite, which is 312 million years, and with argon-argon muscovite, we have this age, which is a cooling ages. So we could find the deformation age of these structures. So we can estimate a progression deformation age range between 312 million years and 289 million years, which gave us a 23 million years interval. So at this moment in Mexico was located on the western margin of Pangea. And other localities of the eastern Mexico had these same ages. So we could find that during these stages, the Paleopacific was starting to the first stages of subduction. So, thank you for listening.
Thank you very much, Luis, for your talk.